Hi everybody, welcome to HPC Tech Shorts again, where we bring you each week to the HPC water cooler here in AWS in HPC engineering, and we talk to the engineers, the architects, and the other geeks who are making HPC, making the cloud the best place to run your HPC workloads. This week I'm joined by Stephen Sachs, who's one of our principal solution architects in the performance engineering team. Hey Stephen.
Hey Bov, thanks for having me.
Stephen's based in Berlin, so it's actually kind of nice. We can both be sitting here drinking coffee for a change, and we're not in two wacky time zones. So,
yeah, almost same time zone.
Yeah. So now this week we're here to talk about an interesting technique that Stephen, a tool that Stephen put together to solve a problem, which was, if you're running OpenFOAM, and then in fact this could be virtually any code on virtually any HPC cluster really, but if you're running OpenFOAM, you're doing a lot of simulations, you're generating an awful lot of data. It's frequently the case that you don't need that data to be online on the cluster all the time. You might want to move that data off reasonably regularly just for cost control purposes. You want to put it on a cheaper tier of data, a cheaper tier of storage. You may ultimately want to put stuff into a life cycle so you can back it up. And the other thing as well is, of course, how many of us have had jobs crash because file systems have been full when jobs, when the scheduled job came up to run. So, and so instead of just having ever expanding file systems, you came up with a pretty cool tool, pretty cool technique for getting data off the cluster into Amazon S3 regularly, right?
Right. So basically what I'm doing is I'm for those who know how OpenFOAM is structured, it's like a lot of small files, and you can make use of that and use that on distributed storage, and then actually take all the small files, pack them together, tar them up, and push that to S3, which basically gives you the performance as if you would having a really, really powerful parallel shared file system, but you don't have it. I mean, this is really, you're just pushing to S3 and then pulling back from S3 for even this texture.
Even though an individual file transmit into S3 is not, S3 is not optimized for single file performance like a Lustre file system is.
Yeah,
but,
right.
In the aggregate, S3 is an absolute beast, right?
Right. So the thing is, if you look at object storage like S3, a single upload will take a lot of latency. So if you do a small file and want to upload that, that's not really performant. But what you can do is if you tar up a lot of small files, and there's a way to actually do that in memory, so you don't have to hassle around with any files. You just dump a lot of files into a pipeline that gets tarred up, and that gets uploaded to S3. That's right. How you get a whole lot of bandwidth out of this upload.
And what's the scenario? Walk us through what's your canonical case? In fact, you built this customer engagement you were doing once upon a time. What's that case? Talk about a generic sort of case.
So if you're talking about something where you're producing a lot of data, which is like in computational fluid dynamics, usually if you're talking combustion workloads, for example, if you're talking anything that's transient, that does a lot of stuff is happening fast. Like, okay, if you have a combustion, there's this layer that's going through the domain that's not coming back again. This is a one time, and you wanna capture that. Now, usually what you want to do in the end is do some post-processing, do videos of that, for example. And for that, you have to write out a whole lot of data while running and having tiny time steps. So you're producing a whole lot of data very, very fast. Now, if you want to get rid of that data and not have that sitting around on your compute nodes, which eventually build full, you either need a very powerful parallel file system or this kind of thing.
Right, and a very powerful, we could do a very powerful file system. But if this is just like a one-way write process of thousands of files, and you're going to do post-processing on it, I don't know, a week later or a couple of days later or a month later, it totally makes sense to push it into S3.
So the thing is, I mean, the obvious other thing you would do is Lustre, right? You just put a Lustre into the cluster and write to that. Now, the thing with Lustre is you get bandwidth linearly with size.
Yeah.
So you have to have like a huge Lustre to get the same bandwidth that you would get by pushing to S3. And when we're talking to S3, like what our tests have shown is that the instance, the EC2 instance, is the bottleneck in terms of bandwidth. So you get as much bandwidth as your cluster can provide when writing to S3.
And like we said before, S3 is actually a beast. So, all right, let's get into this. Enough talking about it. Let's switch over to some scenery here, and let's get to the dirty bits. Okay.
So what I'm showing here is this is what the OpenFOAM test case looks like. So not everyone knows this. So this is Motorbike at 100 million cells. It's a test case a lot of people use. But what I just want to show you is that there is like a single directory for any processor involved in this. And here, this is 288 processors running it because I ran it on 8 nodes. And inside of each of those directories, you will have more stuff. And inside here, you will have individual files, which is like, this is velocity, pressure, and the K-epsilon stuff. So there is a whole lot of small files for this test case. And OpenFOAM is built like that by design. They did that on purpose. Right. Historically, that has been a huge problem, especially for Lustre, because Lustre couldn't do well with small files. No, they got a lot better. They can do that now, but still there are alternatives, and this is here. So this is basically the heart of it. It's like these 2 lines. So basically, what you want to do? Let's start with that tar. This tar actually takes up a file or a bunch of files and makes a tarball out of them, and then pushes that into a pipe. Mm-hmm. Now, the AWS CLI of using this AWS S3 copy, which basically is like it's kind of like a regular copy on a shell, but you can actually pipe something into it, and then it will just upload everything to S3, everything it receives.
Right.
Now, the only catch here, and that's the line above, is if this gets larger. Then I don't know what the limit was, but it was a couple of gigabytes. But if that file actually gets larger, you have to tell it in advance how large the file is going to be. So that's why you do this du.
I was going to ask about that. Okay, yeah, right. This is so that you can prime S3 to potentially.
Right. So S3 knows. Okay, this is the size I'm expecting. And this is how I have to do the upload to get maximum bandwidth for that upload.
So that's the kernel of the technique, and everything else around it is kind of wrapping and orchestration, I guess.
Right. Everything out. This is just selecting files, getting the right files, because you're doing this only for the processor directories that are actually running on that node. And then you just trigger this function tar and upload, and just you can actually have this trigger automatically just by as soon as my disk reaches 80% fill capacity, just upload stuff, right? Yeah. So then also it doesn't matter how long the job is; it's always going to upload, and that's something I added here. Now, how you would usually think about this is like, okay, now I have to write a daemon, and that daemon has to run in the background, and
a cron job or something,
and a cron job or something like that, and you have to make sure that it actually runs and all of that. We actually don't have to do that. We have tools.
Stuff.
We have tools in the cloud to do this. So I wrote up a bunch of boxes. If you could put that chart up.
There they are. Ta-da.
Right. Saying, okay, this is a serverless trigger to do exactly that, to monitor when will your disk capacity hit 80%, and then just do something. And this something in this case is that script which I just showed you earlier.
Right.
So,
and is this script is running on a per node basis, or are you running the script out on the head node?
no, this is on a per node basis. So that's the neat thing about this here. There is no global communication. This is all local. So that's why also you get the full bandwidth of every single EC2 instance going through S3. The first arrow, because that's something that's already there, that we don't have to implement. That is parallel cluster pushing out logs to CloudWatch, which means stuff like Slurm logs and certain kind of metrics are automatically pushed to CloudWatch, so you can watch them there. Now, just watching stuff there is not, I mean, it's not super interesting. You can just SSH into the head node and watch them there. But what you can do in CloudWatch is then you can put an alarm onto that. So if this hits a certain threshold, do something. And that something then this is going through EventBridge into Systems Manager, which says run a command. And that command is trigger the script I just showed you on the instance that just triggered this alarm. Right. So that's basically the setup for the serverless workload. And I mean, just by using that, you don't have to put all the the rough edges. I mean, if you ever want to implement like a cron job and it should always run, and what happens if it gets stuck, and what happens if it doesn't fire, or anything like that, you don't have to worry about any of this, because that's all outside in the service. It's not actually running on the same machine.
Cool. All right, that makes sense. Well, let's see it in action, and then I'm keen to see you take us for a tour of the console and show us CloudWatch and see what those triggers are and so forth. So, how do we do that? I think I need to give you back the
give me that one back. Right.
There you go.
Okay, so I just logged into the cluster again, and there is actually an old run file. So this is what we're going to run now, which basically means download this test case from S3, and then do an MPI run. That's basically it. So we're just running simple foam on 100 million cell motorbike test case. I mean, this is just because I got it laying around.
And how fast is that going to generate how fast is that going to generate files? Like pretty damn frequently, it sounds like.
I wrote it so it will pretty fast start generating files. This is like writing out, I think, every second time step or something like that. So first file is going to be there in a couple of seconds.
Right.
Yeah. Okay.
Right.
So let's sbatch this one. Okay, and I'm just going to go out here. This is just, I had an salloc to pre-warm the nodes, so we don't have to watch the nodes actually boot.
Ah, right. Cool.
Okay. Now, if we look at the Slurm 6 and follow that one. Okay, this is downloading actually. So it's SSHing into every compute node, and there it's downloading the file. That's what it's doing right now. And this now is already OpenFOAM output. So this is OpenFOAM starting, distributing stuff. You can see up here, it's running on those 8 compute nodes, 36 cores each. See, it tells you this is how long it took for those different time steps, and this just means it's generating files now.
Okay.
Okay, so I'm going to switch to the browser now, because I want to show you how this looks like in on the CloudWatch side, and that's a lot easier if you're just looking that.
There you go. Sorry.
There we are. Okay, great.
So here we are in CloudWatch.
Here we are, right? And here are my alarms, like all alarms. If you look here. So for every instance, like I dash something is the instance. So it's eight instances here. I have an 80% alarm, which basically means, oh, here, once this goes over this line, something triggers. And
how did you put all these alarms in? Did you put them in all manually, or did you do them?
No, this is so this is another thing I use in parallel cluster. It's called post install. which basically runs a script every time a node is booted.
Oh, right.
So yeah, every time a compute node comes up, it will register itself with an alarm and say, "Hey, this is my alarm. I also want to be part of that."
Oh, cool. And so that's just like a one-line command in the post install script.
Yeah.
Okay, I'll get you to shows that in a minute. Cool.
And just go look for the XFS because I want that file system. And then select, where you're not going. Oh, this is small now. There's, just select the first couple. Yeah, okay. And here you already see, so this here, the custom, we can even go smaller, go like 5 minutes. So this is like aggregated over every 10 seconds. Every 10 seconds you get another another data point, and this is the percentage of disk usage.
Right. I see. And so you've actually triggered it at 80%, so that at the 80%.
So once it goes to 80%, it
got it.
It triggers, it goes down, and then you see it like going up and down and up and down and all of that.
And how are you selecting the files to get pulled out and tarred off? Like you're selecting them based on age? You're selecting?
I'm selecting everything except for the last one because that might be the one that it's still writing to. So the files are actually also have a name, which is the timestamp. So everything except for the last timestamp.
Cool, that makes sense. That's serious.
So this is going to go up, down, up, down, up, down, up, down all the time.
So that and so that you're actually just going to watch that go up and down and up and down over the entire course of the job.
The entire time. Yeah.
Right.
So the one thing I can show you actually is where this stuff ends up.
Sorry, that is actually there's the magic moment there. That magic moment there is where those curves are dropping down. That's amazing. Yeah, that's really cool.
This is nice to watch, to actually see in action.
That's actually that is the magic moment. Is indeed all of them hit the 80% mark. The script did get triggered and ran, and it's moved data out. In fact, that's happened really fast. Like that's
so
insanely
what you actually see, because this is happening rather fast, is that it actually goes a lot past 80%. So depending on if this cluster is having a good or bad day, it's like between 82 and 87% fill rate until the trigger actually hits and goes. That's why I'm not putting the trigger at like 90 or something like that.
And then it's just pulling all these files.
And I mean, those are not big disks, right? I mean, this is these compute nodes have the default 25 gigabyte disks, and probably, I don't know, like 2/3 of that is operating system and HPC tools that we deliver.
Right. So that's it. So that's fascinating. So and that's just going to keep doing that until the end of the job. So this is absolutely fascinating. We've got so your script, that is the executable script. You've got a post-launch script that gets run on each of the compute nodes as they get added to the cluster, and that really is just a script that subscribes them to a CloudWatch, registers a CloudWatch alarm, right? And then more or less everything else after that happens for free in the sense of no effort from the user. This is really neat.
And the other thing is like you don't need to do any of this automation. You just upload a script, say, here's my trigger. Whenever that trigger hits, execute it, and someone else takes care of that. Right.
And I mean, lots of folks find this weird when they first experience HPC clusters and stuff in the cloud, because it is kind of it's bizarre and different for a while, because there's all these tools out there that you could be using. Like you could be actually spinning this cluster up into existence based on the arrival of some data. So I mean, if you were waiting for a payload of data to arrive from somewhere, and you really wanted to kick off a bunch of processing on it, you could literally have the cluster get created when the data arrives by an automatic trigger that's watching an S3 bucket or watching a POSIX file system somewhere, kick the cluster into life, start working, building the cluster, run all of the jobs and do the work, and then put the cluster away when you're done. There's any number of, you could get pretty imaginative here, but this is a really neat technique. This is
this is just the beginning of one of those pipelines, right? I mean, the triggering, the automatic creation of cluster, that's of course the first thing that comes to mind. I think one of the other things you always have to think about is like cost and performance wise, it does not matter if you run stuff sequentially or in parallel. So you can just spin up a cluster and do post-processing right off the bat as soon as there's anything to post-process. Because you just spin up another cluster. It doesn't matter if you do that after the run or during the run.
Right, and in fact, your post-processing, it's likely you're going to need some different capabilities. I mean, if the output of these things were going to get stitched together into a video, it's likely you probably want some hardware that's got GPUs in it to make some of that post-processing happen much faster, right? That's already earlier than that. I mean, if probably most people running OpenFOAM know this issue. Like, okay, you have your file decomposed for a certain number of CPUs. Are you going to decompose this to run this somewhere else, or what you're going to do? And here it's like, okay, yeah, you just dump this. I mean, you run this on a different machine anyway, so. Yeah. Why not just take the optimal machine for that workload, for that step inside OpenFOAM? Hey, so can we just flip back and can you show us your parallel cluster config file that, and in particular the post installation script? I'm just keen for everybody to see how simple that stuff is.
Sure. So this is post install. Up here, this is just our way of figuring out who am I. And then what you do is like this is the CloudWatch agent that actually pushes the logs. What you're telling it is, take disk, and I actually took memory as well. Because one thing I thought with the next thing it can do is these instances have 25 gigabytes of disk, but they have, I think, like 192 gigabytes of RAM.
Okay.
So on this thing here actually just now pushes the puts the metric and says like, okay, if my file system called the XFS file system, which is the root file system, if that hits 80%, trigger. Yep. So that's post install. If you want to look at the config. To get that post install run, that's just this one line.
Right, and that's the one line I was referring to earlier. So you have an S3 bucket that you've conveniently called OpenFOAM S3. You've got your post install script in there as a single object in that S3 bucket, and the post install script gets referenced in your parallel cluster config file as just a single line like that. Neat. Hey, Stephen, this is really good. I think hopefully this has inspired a few people to think more imaginatively. I think we're going to have you come back and show us some of your other imaginative tricks that people could adopt. We're going to put all of these shell scripts and bits and pieces are all going to be up in this GitHub repo, which I'll also put in the links into the rest of the show. Is there anything else we want to cover before we break off today?
I think that's it for now. I mean, you see, there's a lot of things you can build off of that. This is like the starting point for like building larger pipelines and even optimizing things like RAM disk, for example.
I think we're going to have to do that second stage of this workflow and maybe have get some video coming out of it so that we can see some very cool CFD simulations. Thanks for coming today. I really appreciate it.
Okay, thanks for having me.
And if anybody out there has got ideas that you would like to see us cover on Tech Shorts, different techniques, problems you're trying to solve, we absolutely take reader requests. A number of the videos that we've done so far have been based on that. Our DMs are open on Twitter. Find us at TechHPC on Twitter. DM us, let us know, and we'll see what we can do to fit it into the schedule. Stephen, thanks for coming today. See you on the next one.
Been a pleasure. Bye.
Thank you.